Hi. We were deriving the identification condition for the moment approach or the instrumental variable approach, and the problem was when the matrix expected value of zx prime is square, in this case, then identification condition implies a simple solution because you can invert this matrix, and using the inverse matrix you can write beta as a like expected value of zx prime inverse expected value of zy, something like that. I mean, this from this equation you can multiply inverse of this matrix on both sides to isolate beta 0 on the right hand side. However, it is not possible in the over identification model because this matrix is not square. So it is in general k by m, and k and m may be different. M is greater than k, but k and m may be different. So what we are going to do here is we are going to make this part what the matrix in front of beta or square matrix. We will make the matrix in front of beta or square matrix by multiplying something. So we are going to multiply some matrix which is k by, this is m by k dimension. So if you multiply k by m dimension, then you are going to get k by k matrix in front of beta 0. So A times this expectation will be k by k matrix, and if this k by k matrix is invariable, then you can just multiply the inverse on here and here, and as a result you can get this simple solution. The solution can be derived in this simple way. And then the problem here is I did not explain what is the matrix A. Matrix A is, you may understand the matrix A as the matrix, say, for example, let's go back to an earlier example, like not this one. So for example, if you have these three equations, you may choose two of them, right? You may choose some of them, or you may make a new, like, anyhow, what you need is you need two equations. By combining those three, you may combine and mix three equations and just have two equations in the end. That is, then how to choose and how to combine them to make two equations is a matrix, another matrix A. So the A matrix takes care of the three equations, reducing the three equations into two equations. So that process is in A, and I'm not going to explain details about A right now. It is more of an estimation problem. So in identification, you may use whatever matrix that satisfies this invariability condition, but in the estimation it matters. Then I'm going to do a spoiler. Later, you are going to see that the common choice for the matrix A is this guy. So this is the most common choice of A, and if you plug in this guy into A, then you are going to get a solution, and that is what we are going to use in the estimator. I will explain what we need to assume, why we are using this A, this matrix as A later. And what you need, by the way, what you need here is you need to assume that z prime expected value is invariable. If there is an inverse, already you are using the inverse in the definition. If this exists, then automatically this inverse exists. So this inverse, this matrix is invariable as soon as this matrix is invariable. Mathematically, that is proven. So it's nice and it is easy to understand. It's exactly the full rank condition if you remember, in the classical linear regression model, the full rank condition is that expected value of x prime is invariable, and you are replacing that with the expected value of z prime. So exactly the same rationale. And in the end, the required assumptions for the identification is linearity assumption, which is obvious, and instrument exogeneity. So compare these assumptions with classical linear regression assumption. The exogeneity, which was originally put on x, is now put on z. So z should be exogenous. Instead, x may be endogenous. We do not restrict x. And we have an additional assumption. This relevance assumption did not exist in the classical linear regression model, but it is this. Mathematically, this is rank k, right? So this has a rank of k. And finally, we need to have, we want to have an invariability. So even if it is not invariable, as long as this is satisfied, you have some kind of assumption, right? Already, instead of multiplying this, you may simply multiply this to here. If you use simple a like this, and then if that is invariable, you are good. But later, we are going to involve this matrix into a. So I will include this as another assumption we need for the identification, just for the sake of the discussion of the estimator coming later. And the next topic is the fitted value approach. The fitted value approach is, we discussed the fitted value approach with scalar variable. We have a triangular equation system where the outcome variable y is determined by x1 and x2. Remember, x1 is exogenous, even I'm confused. x1 is exogenous and x2 is endogenous. And simply, we may just combine two variables into simple x. And x2 is endogenous, and the fitted value approach describes how x2 is generated. So x2 is endogenized by this additional equation. So x2 is determined by exogenous variables, which is x1 and instrument, plus another error, and you may simplify this. The problem here is, by the way, remember the y equation, the equation for y is the second stage equation, even though it's numbered as 1, and even though it's the first equation you see. It is the second stage equation because x2 is determined first, and then y is determined later. Or in estimation, you have to estimate this equation first, and then you estimate this equation later. That's why this equation is the second stage equation, or it is called the structural equation. On the other hand, x2 equation is a first stage equation or a reduced form equation, depending on what you prefer to call this. And the problem here is, so in the scalar case, in the previous simple case, it is also very simple. It's having another equation does not cause much problem. It's still simple enough with two equations. But now the problem here is, even though I write this as if an equation, but remember, x2 includes k2 variables. There are k2 variables, and that means this equation explains how all of these k2 variables are determined. So there are basically k2 number of variables, a k2 number of equations in this one line. One line includes multiple equations at the same time, handles multiple variables at the same time. And also, the reason why I use gamma in front of x is because we need to match the dimension. So x2 is k2 by 1, and then you have to have an x1 is k1 by 1. Then gamma 1 has to be k2 by k1, and z2 is m2 dimension, So gamma 2 has to be K2 by M2, right? So when I say this, it's confusing to you, so write that down. So try. Matching the dimensions is nothing. Easy enough. You can do it by yourself. So then we have the triangular equation system. And remember, still, so epsilon is one-dimensional, but psi here, psi is still K2 by one dimension. But the idea is the same. We have endogeneity problem because epsilon and psi are correlated. Some elements of psi are correlated with epsilon. So that's the source of the endogeneity problem. Still, a favorable assumption is that we have z, which is uncorrelated with either epsilon or psi. So z is doing well, but the epsilon psi are not doing well with each other. And the full rank condition, as I assumed here, we need a full rank assumption here. We are going to write it this way. And we additionally assume this is invertible, which is also same as this one. I match two approaches equivalent to each other, and that is the standard. That's the most commonly used way, even though it is not necessary. And when the identification is exact, then it's simple. It will be simple later. And I think I cannot finish this today, so I'm going to resume from this part in the next lecture next week. Have a nice weekend, and remember the homework 1 is posted, so do the homework and see you later. If you have questions, see you in the office hours. Bye.